Most welcome to the introductory lecture of my series on Introduction to Linear Algebra. In this lecture, I shall discuss about the geometry of a system of linear equations. Linear equations are hugely important because we know that the central problem of linear algebra is solving linear equations. Let us begin with two extremely humble equations given by x minus twice y is equal to 1 and x plus y is equal to 4. So let us start with this humble system of two linear equations. I'm pretty sure you all can solve this system of linear simultaneous equations without even taking a course on linear algebra. Now, we can look into this system by two perspectives. The first one I prefer to say as the row perspective, and the second one I prefer to say as the column perspective. The first approach concentrates on the separate equations, that is rows, which is most familiar, and in two dimensions we can do it pretty quickly. Both the equations can be represented by straight lines in the xy plane as given by this, and the solution to this system lies at the point of intersection, this pink point. And you can understand that this pink point is the only solution to this system of linear equations. Now you can simply find out by any method you wish that the point is having the coordinates 3, 1. You can apply any method to find out the coordinate of this intersecting point. But the most preferred, most useful method is the method of elimination. And let me tell you, for large systems, when your number of equations will be very large and number of unknowns will also be very large, the most preferred and most convenient method is known as the Gaussian elimination method. But let me tell you that there are lots of issues about this most effective method, as I told you, that is the Gaussian elimination method or Gaussian elimination algorithm, that we should learn very, very carefully. I shall discuss everything in detail in my successive lectures. Now, the second perspective, that is a column perspective, looks at the columns of the linear system of equations. The two separate equations, as you can see here, actually represent one vector equation given by x into the vector 1, 1 plus y into the vector minus 2, 1 is equal to the vector 1, 4. Now, from this perspective, the problem can be treated as to find the combination of the column vectors 1, 1 and minus 2, 1 on the left side that produces the vector on the right side. Now, this kind of a combination, that is multiplying the vectors with some scalars and taking their sum, this kind of a combination is known as a linear combination of the vectors 1, 1 and minus 2, 1. That means for a specific value of x and y, I will get one specific linear combination. That means each of the linear combinations for a specific value of x and y, each of the linear combination will represent a vector in the same plane. So the question can be rephrased as which linear combination of the two vectors 1, 1 and minus 2, 1 will yield the vector 1, 4. Geometrically, how you will combine the two green vectors to create the pink vector. Combine means which linear combination of the two green vectors will be the pink vectors. The whole idea can be seen as 3 times the vector 1, 1 when added to the vector minus 2, 1, we get the vector 1, 4. That is, if we consider the equation written there, the first vector on the left hand side when multiplied by 3 and added to the second vector in the left hand side, we get the vector in the right hand side. That means 3 into the vector 1, 1 plus 1 into the vector minus 2, 1 is equal to the vector 1, 4, which is algebraically also correct. That means I have got that my x is equal to 3 in this case and my y is equal to 1, which confirms the value that we have obtained for x and y from the row perspective as well. Now, if you look at the row perspective, the figure in the row perspective, you can understand that the two straight lines which are represented here intersect exactly at one point, resulting to the unique solution. But depending on the equations of the two unknowns, 3 cases can occur. The first case is like the case we discussed just now when two of the straight lines intersect exactly at one point, and that results to unique solution of the system. The second case, the two equations may represent two parallel straight lines, and we know that in this case there will be no solution at all. And the third case, the two equations may represent two straight lines which coincide, and in that case all the points on the straight lines will be the solutions. That means the number of solutions will be infinite. So in 2 dimension, these are the possible cases which can happen as per geometric consideration, as per the geometry of the straight lines in 2 dimension. Now, if we extend the discussion to 3 dimension, suppose I have 3 equations with 3 unknowns. Can you tell me geometrically what is represented by a linear equation with 3 unknowns? Absolutely correct. A linear equation with 3 unknowns represent a plane in 3 dimension. So that means the question is, if I have 3 equations in 3 unknowns, we need to think in how many ways the 3 planes represented by 3 equations can lie in 3 dimension. Certainly they can lie in these 5 ways, and you can understand in the first picture the 3 planes intersect at a straight line. That means all the points which are lying on this straight line will be solution of the system of 3 linear equations which is represented by these 3 planes. That means we have infinite number of solutions in this case. Now here you can understand that 2 planes are parallel and 1 plane is intersecting both the parallel planes. But if we consider the points which are common to these 3 planes, we have no point which is common to these 3 planes. That means here we have no solution at all. Now in the third case, all the 3 planes are parallel. So here also we have no solution at all. Now in the fourth case, you can understand that the 3 planes are intersecting at a point. So in this case, we have an unique solution. And in the fifth case, the planes are like that. None of the planes are parallel to one another, but there is no common point of intersection. So here also we have no solution. So depending on your equations, you can have 3 cases. Either your system will have no solution, or your system will have infinite number of solutions, or your system can have unique solution. And if we look at the system from the row perspective, this is the geometry. Now, let me tell you that the visualization or the geometric consideration will completely fail if we work on a large system where the number of unknowns are more than 3. Say, for example, we have a system with 6 unknowns and 5 equations. Now, you cannot plot the equations geometrically because you cannot plot anything in 6 dimensions. So we cannot plot anything geometrically. We cannot understand the nature of the solution geometrically, and geometrically we cannot visualize the solution also. That requires algebraic method backed by our understanding whatever we discussed so far. So we need, whenever we work on higher dimensions, we need proper algebraic method based on the understanding that we have got from 2-dimension or 3-dimension, the visualization that we have got 2-dimension, in 2-dimension or 3-dimension. We need to know algebraic methods or proper algorithms which can tell us about the nature of solution in higher dimension also. That means whether your system has infinite number of solutions, or your system has no solutions, or your system has unique solution, my algorithm should be so designed that I can understand algebraically from that algorithm that what is the nature of the solution and what is my solution, if that exists at all. So from row perspective, this is the geometry of linear equations. Now, the question is how this thing will happen in column perspective. Or in column perspective, when we will say that the no solution, there is no solution of the system, or we can say that there is infinite number of solutions in the system, because we have already understood when unique solution will exist. When a situation like this, what we discussed, what you can see in the right side of your screen, a situation like this happen, then we get unique solution. But the question is when there will be no solution or infinite number of solutions. It's pretty simple. Suppose I have 2 vectors which are lying in the same plane, but the vector in the right hand side, that is the vector that you want to express as a linear combination of these 2 green vectors, is lying outside that plane, that is not lying in that plane. The question is, then can you create this, or can you represent this pink vector, whatever it is, can you represent this pink vector as a linear combination of these 2 green vectors? The answer is no, because any linear combination of these 2 green vectors will yield a vector in the same plane. And since your right hand side vector represented by this pink dot I have represented is lying outside this plane, you cannot represent. That means this case corresponds to no solution. There will be no solution if your vectors or columns or column perspective looks like this. There will be no solution. Now, again, it may happen that the 2 vectors are coinciding like this, and my right hand side vector, that is the pink vector, also coincides with this 2, something like this. Now you can understand, we can represent this pink vector as a linear combination of the 2 green vectors, and not only that, we can represent this pink vector as a linear combination of the 2 green vectors in an infinite number of ways. So if your columns represent these kind of vectors, then you can solve that system in infinitely many ways, or there will be infinite number of solutions. And if I have 2 vectors lying in a plane and the pink vector, that means the right hand side vector, also lies in the same plane, then as discussed above, we will have a unique solution. In a similar way, we can extend the concept in 3 dimension also. And we will see that there can be 3 cases which can occur. Either your system will have no solution, or it will have infinite number of solutions, or it will have unique solution. So the basic issue, if we try to find out the nature of solution of a system of linear simultaneous equation, is whether the column vectors in the context are lying in the same plane or not. But let me tell you, finding whether some vectors are lying in the same plane or not is not so obvious, specifically when your system is very large. Then it's very difficult to find out whether the vectors are lying in the same plane or not lying in the same plane. Not difficult, but I must say it is not so obvious. We need to learn certain method to conclude about this thing. So if I summarize, from row perspective, if we try to analyze a system of linear simultaneous equations, then our task is to find out an effective algorithm that will be convenient and that will tell us whether my system has infinite number of solutions or not possess any solution or possess a unique solution. We need to learn about such an algorithm, such an elimination algorithm. As I told you, that algorithm is the Gaussian elimination algorithm. And from Coulomb perspective, if we try to analyze a system, then our key point of interest is to know whether the column vectors are lying in the same plane or not. So our methods that we will learn in this course will evolve around these 2 perspectives in a major way. A major portion of this course will be developing methods which can answer these 2 things. So that is what we will discuss in this course on linear algebra. Now, a system of linear simultaneous equations can be represented as a matrix equation also, as you can understand that this particular system of linear simultaneous equation can as well be written as 1 minus 2 1 1 into x y is equal to 1 4. So I can write it in a generic way as any system of linear equation in a generic way can be written as ax is equal to b, where this a is your coefficient matrix, this x is the column vector of the unknowns, and this b is the column matrix of the right hand side constants. In this question, your a is this one, your x is this one, and your b is this one. Don't get confused. I have just written x as a name of this column matrix. This x is essentially not this x. So you can if required, you can consider this as capital X also if you get confused. So that means you can write this as capital X also. Here also I can write it as a capital X. So this. So any matrix, any system of linear equations can be represented as a matrix equation also. And you can understand the columns are actually in the linear combination, the columns are the columns of this matrix A. And in this row perspective also, the 2 equations are actually represented by the rows of this matrix A along with the right hand side constants. So what I'm trying to say in a nutshell is this coefficient matrix A along with this column matrix B has a huge role in this entire study. If we learn to understand their properties, if we learn to investigate these matrices, some of the properties of these matrices, then we can very efficiently, very easily find out the nature of solutions. That means now our task will be to learn some properties of matrices, keeping in mind that our objective will be to solve a system of linear equations. So in our next few classes, as the course proceeds, in our next few discussions, we'll be talking about certain concepts which will lead to the solution of system of linear equations, and to be more precise, concepts like linear independence, linear dependence, concept of rank of a matrix. Once we master in those concepts, we can very effectively, very efficiently solve a system of linear simultaneous equations using Gaussian elimination method, or there are some other methods as well. And we also will understand that algebraically how we can infer these two perspectives and how we can connect these two perspectives. So that's it for this video. See you again in the next video. Take care.